Institute of Engineering and Technology.
Hello students, after defining derivative for function of one as well as for two variables and going through its first part of applications in which we have gone through tangent plane, normal line, gradient and directional derivative, today we are going to discuss about how to optimize the function. In this talk, we will see how to define maxima and minima for function of one variable. We will see its graphical interpretation as well as its applications, and later on we will try to extend the idea for function of two variables. We will also try to develop the geometric interpretation for maxima and minima for function of two variables. So let us start this thing by defining or by considering one example. If you are considering a mountaineering or trekking on any mountain, the first picture which will come to your mind is this picture, and this picture is for Mount Everest. Now, if you look carefully, for most of the people, the Mount Everest is the toughest mountain to climb. But is it really the toughest mountain? If you will ask the question to a mathematician or an engineer, answer will be big no. The reason is the toughness of any climbing is decided by many parameters, but actually the biggest parameter in this journey is considered as the stiffness of the slope for the function, which defines the surface of mountain. In case of Everest, the stiffness is not that much as is in this case. Now, so this is the mountain which is Mount Everest, whereas this is K2 mountain. Mount Everest is at the highest point from the earth, whereas K2 is not at that highest point of the earth. But in case of climbing, the toughness level of K2 is far more than that for Mount Everest. The death ratios for Mount Everest is around 4%, whereas the death ratios for K2 is 23%. So from this data only you can imagine how tough it would be for anyone to climb this K2. Now for us at this particular point, it is very interesting to survey this thing mathematically, and for that reason we need to develop maxima and minima for the function, as well as how to consider the stiffness for the function which is defining surface. We will start from the first part, which is extreme values for function of one variable. The first thing which we need in extreme values for function of one variable is critical point. Now, to understand critical point, first of all we need to know at which points on the function our function can be maximum or it can be minimum or something unusual is happening. So in the first case, I am considering a graph of x square, and a point on that graph is moving freely and the red line indicates the tangent at that point. Now if you look carefully, whenever the value of that point is moving from negative to positive, the slope of that tangent is decreasing. Eventually it will become 0 at that red origin point, and then it will again start increasing. So this whole transition is a smooth transition, and we can also see that minimum of this curve is at origin, and try to observe at that point tangent is parallel to x-axis, which means tangent slope is 0. This is the first possibility where we can find critical point. It can be in the reverse order, your parabola can be upside down, and so the red point will become maximum. Now what is happening in the second graph? In second graph I am considering f of x equal to mod of x. I am taking absolute value of x. So if my point is moving from left to right, I can see clearly that initially the slope is constant -1, and at origin you can see clearly that slope is undefined, as there is a cusp. Whenever on your graph you can find a cusp or a sharp corner, at that point derivative is not existing. So at that point in that graph you can see the minimum. Similarly, I can say if the same graph is upside down, that point can be maximum also. So these are two possibilities where I can say a point on the graph can be a critical point. So an interior point C of the domain of the function f is known as critical if f dash is equal to 0 or f dash is undefined. So in first graph f dash C is equal to 0, tangent is parallel to domain, and so it is critical point, whereas in second case f dash is undefined. This is my graph of x square and this is graph of mod of x. Now the question is, if you have a critical point, how to check whether that critical point is function's maximum value or function's minimum value, or something unusual is happening at that critical point. So to understand this whole criteria, I am considering graph of sine function. Now if I move on the sine graph, I can see clearly that at point pi by 2 my graph is attaining its maximum. So that point is one critical point, and then onwards my point will start dropping its value, and suddenly whenever it will reach value 3 pi by 2, again the tangent's value is 0, and then it will start increasing. So by the idea of critical point, I can clearly say that at point pi by 2 and at point 3 pi by 2, tangent is with 0 slope. So these are 2 points where critical points are existing. Now our question that how to identify whether critical point is maximum or minimum. So for that reason, what I will do, I will consider the shape of the graph in surrounding of the critical point. If my shape of the graph in surrounding of critical point is concave down, that means the critical point is maxima at this case. And then if in the surrounding of critical point, if graph is concave up, in that case I can say that the critical point is minima. Now how to check this thing mathematically? So if at any critical point I find f double dash, and if its value is negative, that means that point is maximum or maxima, and function attains maximum value. Similarly, if f double dash is greater than 0, then at that point function attains minima and the value will be minimum. So it is directly related with the double derivative. So in other way you can say that first of all I am finding the point on the graph where first derivative is 0, that means velocity of the point on that path is 0, that means I am in a steady state. And then if you are finding double derivative, which means I am finding acceleration. So if your acceleration is positive, your graph will move in the upward direction, so at that point was minimum. But if your acceleration is negative, your graph will move in the downward direction, so that point was maximum. This is the simple way to remember this condition. But now, is it the only case? Again, answer is no. It may happen that in the surrounding of critical point you have mixed nature. On the half part it is concave down, on the other half part it is concave up. So in that case, f double dash is also equal to c. This is the example. See, if I consider x cube, then what is first derivative? It is 3x square and second derivative is 6x. So second derivative at origin is 0, we cannot conclude anything. So this test will become inconclusive. But now this will also give rise to two different possibilities which are known as point of inflation and undulation point. To understand this point of inflation and undulation point, to understand first part, point of inflation, I am considering the same graph. The definition says that if critical point C is such that f double dash is equal to 0, second derivative test is inconclusive, but triple derivative is not equal to 0. As in this case of y equal to x cube, if I find the triple derivative, it will be 6, which is non-zero, which clearly indicates that this is the point of inflation. Now, you will see that what do we mean by point of inflation? Graphically, you can identify the point of inflation by two things. The first thing is the graph is changing its nature at this critical point from concave up to concave down on reverse way. The other way is if you fix this point and if you rotate the graph at 180 degree, it will give you the same graph after this transition. The another case is undulation point. Now if you look carefully in x raised to 4 also double derivative is 0, test is inconclusive, but here the function is not changing its sign, whereas in the previous case function was moving from negative to positive value. So at this point where double derivative is 0 and function is not changing its value, that point is known as undulation point. Now there is one exercise for all of you. You should consider a graph of x into sin x. The graph of x into sin x is something like this. Now if I focus particularly on this section only, -1 to 9, then what will happen if I fix the point and if I take the tangent? Now exercise for all of you is that you should trace what is derivative of this function. You should pause and ponder at this stage, and later on you can check what is your answer. So after considering the whole process, now I can clearly identify 4 points B, E, D and G. Now at these points, these are the interior points of the graph where function attains critical values, and I am considering 2 endpoints also, as I am considering a particular part of the graph, and the endpoints A and F, they represent x equal to -1 and x equal to 9. So if you do this practice, if you float your point on this graph, you can see clearly the value of tangent is changing continuously. Now you should know where it will attain maximum, where it will attain minimum, and which points are only critical points. So if I plot the graph of the derivative of the function, it is represented by orange graph, and here you can see clearly that whenever it will cross x-axis, those points are points of zero slope. So those are critical points, and I particularly highlighted 2 points with red color. They indicates minimum and maximum respectively, and so the derivative of the function is x plus x into cos x for the same range -1 to 9. So first of all I will take critical point. Now in case of function of 2 variables, it will be a bit different than function of 1 variable. Now as we are dealing with the surface, in this surface you can see clearly the minimum value is existing at the point origin. This is a graph of x square plus y square. So what I will do, I will fix that point and I will find a tangent parallel to x-axis on this surface, and you can see clearly here tangent at point origin is with zero slope. Now if I do the same process but with help of y-axis, then again I will see clearly that the tangent is moving on this surface, and whenever it will reach this point, the tangent is parallel to y-axis and so with zero slope. And if I combine both of these tangents, see, I need to take tangent with respect to x, I need to take tangent with respect to y, and what I will do, I will identify where these 2 tangents are simultaneously parallel to xy plane, and that point will be your critical point. So here at origin you can see clearly that a tangent plane is on xy plane. In other words, you can say it is parallel to xy plane. So the property is remaining same. Tangent property is parallel to domain property, which gives you the critical point. So now I can define critical point. The definition of critical point is this: interior point C in the domain of the function z equal to f of xy, where both f sub x and f sub y are 0 or any one is undefined, is known as critical point. Now there are some different cases also. If I consider this case, here you will see that if I fix the point origin and if I consider derivative with respect to x, or if I take a tangent which is moving parallel to x-axis, then at origin it is with zero slope, but you will see clearly that here the graph is attaining its minimum, whereas if I take parallel to y-axis, for the same interpretation graph is attaining its maximum. So this is also a critical point, but here something unusual is happening which we will discuss in the upcoming time. So clearly you can see here it is maximum on this and previously it was minimum. So on the same point you have two different possibilities. It is minimum in one direction, it is maximum in another direction, and so clearly at this junction you can see the shape of this structure, and this structure is particularly known as saddle. A saddle is a sitting arrangement which we are using for the horse riding. This is our sitting for horse riding. This is the reason why it is also known as saddle point. Now let us consider another case. Now this is something different from saddle. See, in saddle parallel to x-axis our graph was minimum, parallel to y-axis our graph was maximum. But in this case what is happening is, if I move parallel to x-axis or if I move parallel to y-axis, on the whole of these two fundamental axes my slope is remaining 0. And at origin you can say particularly our tangent plane will be parallel to xy plane, but at all other points on the surface our tangent plane will not be parallel to xy plane. So all other points are non-critical points where the origin only is the critical point. You can see clearly I am floating tangent plane on y-axis, the slope is changing, and then if I float tangent plane on any random value it is not parallel to xy plane. So this is whole idea about these two different cases. So how to detect this thing? How to check whether my critical point is maxima or minima for function of two variables? So if I look carefully at these two cases, I can say that I need to introduce something which is in between these two, a random partial derivative of two order which is f sub xy. And then if I will take a parameter which is known as Hessian, I will get the correct idea about what is happening in the neighborhood of the point. We have seen three different cases. In x square plus y square, in the neighborhood or in the surrounding of critical point, the graph was continuously dropping, so that point was minimum. In the first case over here you can see at the saddle point our value is decreasing in one direction which is parallel to x, whereas it is increasing in other direction which is parallel to y. Whereas in the third case we cannot say anything by considering x and y axis. So the first task for us over here is to check what is happening in the neighborhood of the critical point. So that can be done with help of Hessian. Hessian is a mathematical term defined by f sub xx, f sub yy minus f sub xy whole square, which gives us the simultaneous nature of the surface in the neighborhood of C. Simultaneous nature means it is with a same nature. If it is decreasing in the neighborhood of x, then it is decreasing from all possible directions. If it is increasing in the neighborhood of point, then it is increasing in all possible directions. So if Hessian is greater than 0, then and then only we can say the simultaneous nature is existing in the neighborhood of C, and so function can attain maxima or minima at C. And then in particular, if Hessian is positive, and now we can take acceleration in any random direction. So I can choose with respect to x or y. If it is less than 0, then again acceleration is negative, and that means our point is at maximum height, so it is maxima. And if acceleration is positive, point is minima. But if this Hessian is negative, that critical point is saddle point. You need to note these three values: maxima, minima and saddle point. Saddle point is somehow analogy for point of inflation in function of two variables. Let us consider one example. If I consider a function x cube plus y cube minus 3xy, and if I want to find extreme values, the first step is to identify critical points, and for that I am taking f sub x, f sub y, I am equating it to 0. That means I am finding graphically a tangent line which is parallel to x axis, tangent line which is parallel to y axis, and then I am combining both of this, which gives me that x equal to 0 or x equal to 1. These are two lines on which it is happening. And then if I plug in the values into f sub x or f sub y, it gives me value of y which is 0, 1. So intersection of this gives me 2 points. So these are only two critical points where my function can attain maxima or minima, or it can be a saddle point. Let us verify that using Hessian. So if I calculate Hessian for this, I need f sub xx, f sub yy, f sub xy, which are respectively 6x, 6y and minus 3. So value of Hessian is 36xy minus 9. And therefore, the value of Hessian particularly at first critical point is negative, which means at origin my function is attending saddle point, and at point 1, 1 second critical point its value is greater than 0 and f sub xx is also greater than 0, and that means it is minima. So now clearly you can see the whole structure graphically. If I consider graph of this function x cube plus y cube minus 3xy, and if I plot the contour map in xy plane, I can see clearly 2 points, origin and 1, 1, at which I am finding critical points. See, contour maps are also helpful into identifying whether there will be any critical point on the surface or not, and that is how you can find critical points on the contour map by intersecting contour maps, or in a particular region if they are shrinking at a particular point, there can be a point which is minima or maximum. Now I will focus on these 2 points 0, 0 and 1, 1. These are points where maxima and minima are existing. Now I am taking tangent plane at this point, and then if you move point on the surface, you will see clearly that these are only 2 points where tangent plane is actually parallel to xy plane. I am taking the same tangent plane on contour map. If I float the plane on this contour map, parallelly my tangent plane is actually moving on my surface. I can see clearly that it is only parallel to xy plane at 2 points 0, 0 and 1, 1. I will take the same thing on 3-dimensional structure also. See, like this. So I am taking contour map, I am taking 3-dimensional surface, and then the plane is floating on this surface. You will see clearly that at origin and at point 1, 1 only it is parallel to xy plane. This is how you can identify whether your critical point is minima or it is maxima. Now again one exercise for all of you. It was very easy whenever we are considering the whole surface at a time, but in real life it will never happen. We need to consider a section only for the surface, and we want to find maxima and minima. So now what I will do, I will take a surface and I will restrict the domain, and then I will check what is happening to the surface in terms of its maxima and minima. So for that reason I am considering equation of 2 plus 2x plus 4y minus x square minus y square. Clearly by zooming in you can see over here at the peak point of this I am taking maxima, or it will be maxima. Now if I chop it by a plane and if I restrict it in the first quadrant only by boundaries x equal to 0, y equal to 0 and line y equal to 9 minus x, this will be the structure which will remain with us. And now I want to find maxima and minima in this structure. So what I will do, first of all, I will consider a point which is critical point. That means I am taking interior values. Now I am taking x-axis. So on x-axis I have 1, 2 and third point which is actually origin. And then I will take y-axis. If I take boundary which is y-axis, I will get first point over here, I will take second point over here, and finally I will take line y equal to 9 minus x. So I will get point over here. So that means these are the points where maxima or minima can exist. So now we need to focus on this and we want to consider the whole concept. So this is 3D image, whereas here I am plotting it with help of 2D projection. So you can see clearly, if I take the top view of this structure, I will get this many critical points, which are 7 in number. So this is what is happening graphically. Now what I will do, I will focus on this 2 image only, and I will try to figure out how many critical points are there and which one is maximum, which one is minimum. So I am taking critical points from interior values, or how to find critical point which is in the interior part. For that we are taking our regular calculation, f sub x equal to 0, f sub y equal to 0, and this gives me first critical point 1, 2. Now I am taking boundary points. So on x axis, value of y is 0 in the function, so it will reduce through function of one variable, and then I will take derivative equal to 0, which will give me point 1, 0. Similarly, in y axis I am taking x coordinate 0, and then I am taking f dash equal to 0, which gives me point 0, 2. And then on line AB, means line y equal to 9 minus x, it gives me value 4, 5. Here in this case, to calculate this, we need to replace y with 9 minus x everywhere in the function, and then I am taking derivative equal to 0. Finally, the end point of this triangular region 0, 9, 9, 0 and 0, 0. So these are 7 critical points in our consideration. So now no need to find second derivative or to do any Hessian here over here. Okay, here what you can do, you can list out the points, you can find functions value directly and pick the maximum and minimum from that. So clearly we can see that the maxima is existing at 1, 2, because the value which is maximum from this list is 7. So it is maxima, and minima is existing at 9, 0, as the minimum value over here is minus 61. So I hope all of you understand this whole concept of derivative and applications of derivative, particularly optimization. And in future we are going to discuss now integration for function of one variable and function of two variables and their applications in detail. Thank you.
LJ Institute of Engineering and Technology.